All right, our next speaker, we'll just move right on here, is John Baez, who's going to tell us about coarse-graining open Markov processes. We just say again for anybody who's just joining us, if you have questions during the talk that are urgent and short, you can ask them in the chat or raise your hand, and I might ask the speaker, or other people might be able to answer them. Otherwise, you can save them for the question time at the end. All right, take it away, John.
Okay, thanks. Well, it's a great conference. It's really nice to see how we're starting to develop a kind of chain of reach going from the very pure to the very applied. I hope everybody goes to the industry talks tomorrow, which start at 1640 UTC. There'll be 8 quite short talks about different companies or organizations that are using applied category theory. And so the way I see it is that the people at the pure end are generating these paradigms and these methods of modeling and sort of hawking them, touting their virtues. And then people further towards the industry end can decide which ones they want to use and maybe provide feedback.
Yeah, I'm only bored on the side.
Hello. And so we'll get a nice research feedback loop going here, which seems to be the key to any good applied science. So I want to talk a little bit about how category theory gives new ways to model open systems. Maybe they're not so new. I think maybe all of my stuff that I just talked about could be fit into David's framework. So this is maybe more zoomed in on one particular, well, it's definitely zoomed in on one particular kind of open dynamical system. So they're called continuous time finite state Markov chains, where something is hopping around randomly between a finite set of states as time passes continuously. But because that's such a mouthful, I'm just going to call them Markov processes, which is really a name for something much more general. So together with Brendan and Blake Pollard, we wrote a paper on Markov processes a while back, which limited the class of Markov processes that could be studied, and also used this Coast-band framework, which turns out to have some problems with it, which are corrected by my student Kenny Courser. Kenny Courser, this work is probably best seen in his thesis, which isn't quite on the archive yet, but you can grab it here at this URL for now. Open Systems, a Double Categorical Perspective. And in specific, the application to open Markov processes is a paper that he and I wrote. Kenny needs a job, so please consider hiring him when you see how great his thesis is. So the basic game plan here is you start with any old kind of system. So I'm going to talk about these Markov processes, any kind of dynamical system, for example, but here's the one. So a Markov process is really just basically determined by an n by n matrix, if you want to think of it in a low, where here you have a 4 by 4 matrix that's describing how the probability of being in any one of 4 states, A, B, C, or D, changes with time. So PA of t is the probability of being in state A at time t, and in a linear way, depending on the probabilities themselves. And so, for example, this 1/2 here says that if you start out in state A, then you tend to hop over to state C, if I'm getting it right, with a probability equal to, well, with the time derivative of your probability is equal to 1/2 times the probability that you're at state A now. So you leak over from state A to state C. Because you're going away from state A, then the probability that you stay in state A decreases, and so this needs to be a negative 1/2 here. So if you work out the restrictions on things that need to hold, the columns, each set of column entries has to sum to 0 to make probability, the total probability of being somewhere or other, that is the sum of all these 4 numbers, not change with time. And the off-diagonal entries are the rates at which you hop from one state to another. So those are non-negative, but those 2 restrictions together make the diagonals be non-positive. So that's what a Markov process is in a nutshell. And there are tons of books, textbooks on these, and lots of wonderful theorems about them. It's a great subject. So what do we do with them that's new? Well, the very first thing we do, which is not completely new, but it's very important, is to draw a picture of them, which is much better than drawing that stupid matrix that I wrote down. So here's the same data conveyed on top as on bottom. So here are our 4 states, or these green circles. These rates, these rates of hopping from one state to another are just labeled edges. And if we're missing an edge, we call that a 0. And as I said, the diagonal entries, which are the rates at which you hop away from where you are, they're determined by the data in the pictures because the columns sum to 0. So you don't even need to draw those. So this is a picture of a Markov process. And people who work on Markov processes always draw these pictures. And part of my shtick these days has been realizing that and pointing out that people in various applied subjects use pictures as their own private tools, which they don't think of as mathematics. They think of as the stuff you need to understand the mathematics. But we know, as category theorists, know that it's mathematics too. So we should just learn what these folks are doing. So now the next step is to open it up, by which I mean consider open Markov processes. So if you want to make Markov process out of little ones, this pictorial intuition is very helpful because you want to stick together the little pictures to form a big picture, but a part of a picture is going to have some loose ends, so to speak, where you are getting ready to stick it onto the other parts of the picture. So we can describe those using basically what's a cospan of finite sets. So we have a set here and a set here with maps into the set of states of our Markov process. And then on top of that cospan of finite sets, we have the apex set is equipped with the data of a Markov process. And then if we pick functions of time for each of these brownish dots here, which we could call inflows and outflows, then we can add terms to our equation, which describe how probability can flow in on the inputs and out on the outputs. And just for bookkeeping reasons, we put a minus sign in front of the outputs so that when we actually stick these together, one guy's input is the other guy's output. And so what's flowing into me is what's flowing out to you. It just works good with that minus sign there. So we look at this open Markov process concept, which is already, I think, fairly new. But once you do that, then of course, you realize that what you're doing here is you're wanting to build yourself, at the very least, a category where these open systems, in particular here, these open Markov processes, are morphisms. And so you can compose one with another if the output set of one matches the input set of the other. And you can stick them together this way. Notice here, since from this 4 is getting mapped to D here and getting mapped to E here, when we glom them together, we're really doing a push out. And so D and E are getting identified, and we can call it whatever we want. I'm calling it H. So we are composing cospans via push out, but then the cospans are decorated with this extra information of this directed graph with edges labeled by numbers. So we could at very least get a category there, but there's much more to it than that, because of course, you should always consider making your category of open systems monoidal. As David recently, just a minute ago, pointed out, you can stick systems side by side. So we could take 2 of these morphisms, set them side by side, and that's giving us a monoidal category, which is going to be symmetric monoidal too, of course. But you shouldn't forget that there's more to life than categories. There's double categories. And so the point is that we're treating open systems as morphisms, but an open system is really a kind of a thing. And whenever you have a thing, you should look at morphisms between things. So now we have to look at morphisms between these things that we are considering morphisms. And that turns out to be very useful. So for example, if here I have above one open Markov process and down below I have another one, we could study some kind of map from one to the other. And Markov process theory, the kind of maps that they talk about the most are called coarse-graining. because they're very interested in simplifying models of situations. And so you might have this Markov process here with two states B1 and B2, and you might decide, I don't really care about the difference between B1 and B2. I'll just call them both B and get a simplified model. Now, this issue of coarse graining is very subtle and complicated and interesting, but if we want the most well-behaved sort of coarse graining, where everything works really nicely, what we would like would be able to solve the differential equation given by our open Markov process here, and then coarse grain the answer, or coarse grain the initial data here and the input and output functions, and then solve it and get the same thing. That's a very strong restriction to say that you can simplify your model and sort of encounter no friction or errors due to the fact that you've lumped together several states to one. And so that imposes these restrictions. For example, these two numbers have got to be the same, in this case 6, because what we're saying is that your chance of the rate at which you hop out of here to here, it better be the same as hopping from here to here, because you're going to wind up in the simplified model not knowing which one you're in. You're just calling them both B. So we wouldn't know what to do if these two numbers were the same or weren't the same. Okay, but notice we don't require that these two numbers be the same. These inputs to two states that we're identifying, what we're doing there is we're just adding them up, because we're saying that, like, you have per second you have an 8% chance of hopping here and a 3% chance of hopping there. Well, that just means that with an 11% chance you're hopping to one or the other, and so we just add up those numbers there. Don't take the percents, I said, too seriously. These are just rates per time. And then also these numbers, these just completely go away, because if you're hopping back and forth between B1 and B2 in the simplified model, it's just the same as if you're staying here. So the people who work on Markov processes think about coarse graining, and this is a particular well-behind kind of coarse graining. So putting all this together, we get ourselves a symmetric monoidal double category that includes all the junk that I just talked about. So the objects are finite sets. So those are like these guys here. Horizontal one cells will be these open Markov processes. So those are a co-span of finite sets. For technical reasons, I'm going to want those arrows to be injections. And then a Markov process on the set of states X. So you can think of a Markov process as an X by X matrix of real numbers with columns summing to 0 and off diagonals that are greater than or equal to 0. Or you can, if you don't like matrices, you can think of it as a linear map from R to the X to R to the X with those same type of properties. So that's what I've been showing you. And then we're going to have some vertical one morphisms, which will just be functions between finite sets. And then the exciting part are the two morphisms, which should include these coarse grainings as a special case. And they will be commutative squares like this, where, again, for technical reasons, I'm going to want these each of these squares to be a pullback. And then the exciting part is that we want to have this equation holding between the matrix H and the matrix H prime. So when you have a map from one finite set to another, X to X prime, it gives rise to a linear map between the free vector spaces on those finite sets. And we want to have this commutativity condition here, which says basically that it amounts to saying you can do your Markov process up here and then down, or you could project down and then do your Markov process here. So this equation here, written very nice and concisely, is the thing that was imposing all these things that I was spouting off about how these two numbers have to be the same, and these two, when you add up gives you this, and these go away, all that junk, which people in Markov process land know all about, winds up just boiling down to this equation here. So that's a two-morphism of open Markov processes. And then, well, you can tensor these guys in just sort of the obvious way. You take the disjoint unions or coproducts of your sets, and you take the direct sum, a block diagonal sum of your matrices. So you stick pluses all over the place to make your double category symmetric monoidal. Okay, so now you've got this glorious double category. So what do you do with it? Well, of course, you want to use functors to map out of it into other categories, which will describe how your Markov processes are behaving. So if open systems are morphisms, then functors describe their behavior, what they do. So for example, there would be some functor that completely describes what an open Markov process does. It would just map the Markov process to some dynamical system. Could be in some large category of dynamical systems of the sort that David is describing. Or you could do something a little bit more destructive and therefore more interesting. Namely, you could black box it, which is, for me, means describing only the relation that holds between inputs and outputs in steady states. So by a steady state, I mean, you've got these functions, I1, I2, and I3 saying how much probability is flowing in, and one here saying how much probability is flowing out. If you hold those all constants, then there will typically, and there are theorems about this, be certain solutions of that differential equation I wrote down, where the probabilities at all these states here are also constant. So basically, no probabilities are changing, but still, nonetheless, something sort of is happening, because probability could be flowing through from here to here. So it's like you've got water flowing into the tap into your bathtub and flowing out the drain, but at a constant rate. So in some sense, nothing is happening, but in another sense, there's flow going on. And so it turns out that when you black box this system, what you do is you ask, what's the relation that could hold in a steady state between the inflows here, here, and here, and the outflows here and here. And also, in fact, you have to attach certain probabilities here, 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 and here. So you get a relation between numbers that holds in steady state. And so there's a black boxing symmetric monoidal double functor that does this. It goes from our double category Mark to another double category that's just all about linear relations. It has finite dimensional real vector spaces as objects, relations, that is linear subspaces of the direct sum as horizontal one cells, and linear maps as the vertical one morphisms. And then the squares, the two morphisms, are just squares that basically say that the square commutes, which, well, or not, which really, you could write it out this way. So the most exciting thing about this black boxing functor is that it takes a Markov process and black box it and gets a linear relation, describes its steady state behavior. So to prove that theorem, that there is this symmetric monoidal double functor and that there is this symmetric monoidal double category, we actually had to do a little bit of work. So in category theory, I think more than any other subject in mathematics, one tries to act as if one isn't really doing any work at all, except, of course, coming up with beautiful definitions that are like a real lot of work to understand. But then, like, once you understand them, you're so brilliant, you can just go theorems, or just no work at all. That's sort of the opposite of the attitude of most mathematicians, right? Where everyone's supposed to understand what a group is, but then, like, classifying the finite groups is like not so easy. But I just want to tell everybody, mainly the very category theorists, that it actually is good sometimes to do a little bit of work. I know it sounds like heresy, but so for example, to construct this double category, we needed to actually do some work. We needed to use the fact that the category of finite sets was something called an adhesive category, and that this so-called Van Kampen cube condition held. Now, this is a kind of thing that people I think of as like true category theorists. They can like remember this kind of stuff or express it in some more sophisticated way. But for me, this is always like beyond the limit of my desire to learn category theory until I actually needed it. So, it says some wacky thing here, right? If the top and bottom faces are push-outs, and the left and the back one are pullbacks, and two of these arrows are monic, then the right and front one are pullbacks as well. I can never remember that. That's why I had to put it on the slide. But the interesting thing is that turns out to be apparently what we actually need to get Mark to be a double category. So now maybe that just means we're doing something stupid, right? Because it probably shouldn't be so much work to prove that you've got a double category. But anyway, maybe someone else can prove that later. So that's an example of a double category of open systems for you. Thanks.
All right, thanks very much. Let's thank John virtually, silently, with our claps on the chat. Are there any questions?
Let's see, I haven't been reading the chat, so if there are chat questions, I would not yet
There were
know
some
about
questions,
them.
but I think they were mostly answered.
Uh-huh.
Anyone who didn't get their question answered, feel free to ask it.
My talk must have been too clear. I should have said something really incomprehensible. I will just say, by the way, that that this decorated co-span framework that Brendan cooked up in his PhD thesis, it's really great, but it's actually, there's something really wrong with it. There's a real mistake that it doesn't work in most of the examples that I've used it for. And so, so it's like a really niggly, nitpicky, irritating mistake, but it's a mistake. And so if you're at all interested in the decorated co-spans, you should read Kenny's thesis, because right now that's the place that goes through and explains in the simple case of the category of open graphs, what that mistake is, and then how to fix it as well. I should have talked about it.
Can you put the link to that thesis somewhere on the chat or on the Zulip?
Yeah, I will. I may already have, but I'll do it again. Yeah. Yeah. If I'd been more organized or something, I might have given a talk just about that, because I think there's some interest in that. Okay, but I won't.
Any other questions? If not, yeah.
Yeah, well, I guess I could ask. So the idea that the category of finite sets is adhesive, does that mean you could replace it by any other adhesive category and get some kind of similar system, or what would change, or would it be interesting at all?
That could be interesting. I mean, very simple example of how it could be interesting is that in real life applications of Markov processes, people often don't want to just have finite sets of states. Then even more analysis shows up, but you might want to tackle that sometime and then get some kind of nice adhesive category of spaces or measurable spaces or something like that. That's the example I think of. Okay.
All right. So if there are no more questions, then let's thank John again.